Okay, we're going to pick up where we just left off in our discussion of centripetal acceleration and consider non-constant velocity, which means we've got both centripetal and tangential acceleration. Non-constant velocity. Okay, so let's think about from our derivation before, what's wrong with it and what do we need to change? Okay, so this initial sketch here is still okay, but if our velocity is not constant, then this expression for delta theta equals v2 over r is no longer true, okay? And so we need to write this in a different way. And then our displacement vector in terms of delta theta is still correct, but the way that delta theta depends on time is different, and so then this time derivative is going to be different as well. Okay, so we're going to get some new space and write this again. Okay, so it's still the case that x equals r cosine theta, and that y equals r sine theta. I keep writing these as delta theta because I want you to remember that you've gone through some angle delta theta. Instead of r delta theta equals vt, we're going to have that r delta theta is the integral from time 0 to time t v of t prime dt prime. Okay. Notice this velocity, so we're assuming that it stays in a circular path. Okay, so this velocity, this is really the speed, not the velocity, although it can be negative, but it's the magnitude, I guess, of we're assuming a direction for the rotation, but then this is the magnitude of that velocity, which can be either positive or negative as it goes around the circle. Okay, and so since that velocity is changing, it's not just that r delta theta equals vt, it's that we need to integrate the velocity to get that r dt. And you can think about for some very small delta theta, it would be true at any moment, right, that for a very small delta theta, that r delta theta would be vt, and then if we added a bunch of small delta thetas to get our total change in theta, that's basically the definition of an integral. So that's where this expression comes from. Okay, and so that means that we can write x as r cosine of 1 over r integral from 0 to t v of t prime dt prime. Remember again that this t prime is not a derivative, it's a dummy variable that we're using because we're going to have these two different t. Okay. All right. And then our dx dt, which we're going to need in order to find the velocity, is going to be the time derivative of this expression, which I'm just going to give you without showing the details of that work, is r v of t over r sine 1 over r integral 0 to t v of t prime dt prime. There should be a negative sign out front here. And this is basically a result of the chain rule again. This is why this is the case. All right. And so then this is negative v of t sine 1 over r integral 0 to t v of t prime dt prime. Okay. So actually this, as it turns out, looks pretty much like the velocity expression that we had before, which was not necessarily obvious, but does turn out to be the case. However, things get a little bit more complicated when we try to find the acceleration. So if we take another derivative of this same expression, now we need to use the product rule. And so we've got, I'm going to do something that's maybe a little bit counterintuitive, but I'm going to take the derivative of this part first. So I've got negative v of t. I've got another factor of v of t out front from the chain rule. Then cosine, I'm not going to write this whole thing again, but this whole thing is inside my cosine. And then by the product rule, I'm next going to take the derivative of this first term. And so that is negative dv dt sine of this whole thing inside the derivative again. Okay? So that means that my ax is negative v squared cosine of that whole thing, same as before, minus dv dt sine of that whole thing. Okay? And we can notice that in fact this cosine term is x over r, and this sine term is y over r, right? Since x is r cos delta theta. And I didn't do this same derivation explicitly for y, but you could plug in that same integral, right, using this here. Okay, so we can write that this ax is negative v squared over r times x over r minus dv dt y over r. Okay. And now by a very similar derivation that I'm not going to show all the steps of, we would find that the acceleration for y is negative v squared over r times y over r plus dv dt x over r. Okay. And so we can rearrange this and now write this as a vector. So we're going to write this as a vector. We've got a is negative v squared over r x over r I hat plus y over r j hat plus dv dt negative y over r I hat plus x over r j hat. Okay. And so this first term turns out to be exactly the same as the centripetal acceleration we found in the previous derivation. And then this second term is what we call the tangential acceleration. And so if you look, you'll find that this first term points inward toward the center of the circle, and that this second term points tangentially to the circle in the direction of change in dv dt, or in the direction of motion, and then the sign will be given by this dv dt. So that's where this expression for our tangential and centripetal acceleration comes from. I'm accidentally erasing things, sorry. Tangential acceleration here. All right, cool. That's it.